Good morning to one. Good morning to one and all. So once again, welcome to VLSI class. So in the last class, we discussed about output circuit and LDI by dt noise, right? And how to reduce the noise. We will discuss in the last class. Now let's go to the next topic, that is on-chip clock generation and distribution. Okay, on-chip clock generation and distribution. So this is the topic. So as we know that for a human being, the heartbeats are very, very important. Okay, similarly, for digital system, the clock signals are very, very important. So the clock signals are the heartbeats of the digital system. Okay, and the stability of the clock signals are highly important in this case. Okay, in the digital system, the main stability is very, very important. Okay, clock signals are the heartbeats of the digital system, but the stability of the clock signal is very important in case of digital system. So the ideal, basically what happens is the ideal clock signal should have the minimum rise time and fall time. That is the first thing you have to remember. Okay, the ideal clock signal should have minimum rise time and fall time, and this should have second time is they should have specified duty cycle, and they should have the zero skew. Okay, these are the ideal clock signal. These are the proper the clock signal must have the following 3 point important here. That is the minimum rise time and fall time of the clock signal. Similarly, second one is they should have a specified duty cycle, and they should have zero skews. Okay, these are the 3 points. But practical clock signals, we have non-zero skews. Okay, non-zero skews, and there is a noticeable rise and fall times, and also the duty cycle varies. Okay, these are the practical clock signals. So there is a difference between the ideal clock signals and the practical clock signals. Okay, so these are the main important things you have to remember. Okay, similarly, for simple technique for this on-chip generation of the clock signal is so how to generate this on-chip clock generation is by using a ring oscillator. Okay, by using a simple on-chip clock generation circuit is nothing but a ring oscillator. It is showing on the figure. So this is the ring oscillator. Okay, so this type of clock circuit basically this type of circuit is used in basically it has been used in the low microprocessors. Okay, low end microprocessors. So these are that is a simple ring oscillator circuit. So has been used in low end microprocessors. Okay, so in this case the generated clock pulse in basically is process dependent, and they are unstable. Whatever the clock signals are generated from this ring oscillator, in this case, they are process dependent, and also they are unstable. So what to do now here? So we require a separate clock chip. Okay, we require a separate clock chip that has been used for high performance in VLSI circuits. Okay, that can be used in the high performance VLSI chips. Okay, that is the main thing you have to remember. So we require a separate clock chip, so that is used for high performance VLSI chip families. Basically, we are going to use VLSI chip families. Okay, and in this case, in this clock chip, basically these clock chips uses the what happened now? These clock chips basically uses the crystal oscillator. Okay, so these that is the high performance VLSI chip families uses crystal oscillator as a clock chip. Okay, the clock chip uses the crystal oscillator. Remember that point. So because as you know that this crystal oscillator produces very good stability. Yes, stability of the frequency. That means frequency will be very stable in case of crystal oscillators. Okay. So now let's go for the next one. There is this type of circuit here. These are the circuit diagram of basic crystal oscillator circuit. Okay, we are using the crystal oscillator circuit in this case. So we know that this is the crystal. Okay, and the equivalent circuit of the crystal is nothing but a series resistance circuit. As there is also all of you already you know that one. The crystal oscillator is nothing but a series RLC circuit in this case. Okay, so in this case the crystal requires a low load impedance. So therefore, across load impedance across its terminals basically. Okay, the crystal requires low load impedance across its terminals. Remember. So therefore, so in this so already we know that the crystal consists nothing but a series resonance circuit. Okay, the series RLC circuit basically. Okay, so in this series resonance circuit, the internal resistance determines the frequency. Okay, response basically determines the resonance frequency. Basically, we can call. Okay, it is a resonance frequency produces the series resistance the series internal resistance of the series resonance circuit determine the resonance frequency. So in this circuit, okay, in this circuit, the crystal basically nothing but series resonance circuit. There is a series RLC circuit. So higher the resistance, when so resistance is very higher. For example, the resistance is higher, the frequency will be lower. Okay, in case of series resistance circuit, resistance is higher, lower the frequency. So therefore, at the the load at the terminals of this crystal as considered effect. Okay, whatever the load is connected across the terminals of the crystal will also produce some considerable effect on the frequency and also its stability. So that is also very, very important. Okay, not only the internal resistance across the output load, that means across the terminals of the crystal, whatever the load you are going to connect here. Okay, that is also effect on the frequency and also stability. Okay, so therefore, and we are having, see, just another circuit in this case is we are having the inverter across the terminals, across the crystal, okay, which provides the necessary voltage difference. Okay, this provides a necessary voltage difference. For example, if the voltage is high, we are getting the voltage is low here. Okay, so there is whatever the voltage across the two plates in this case, but produce the voltage difference, right? So similarly, the external kept inverter we are having here. So this inverter provides amplification to drive the clock loads. Okay, it provides the amplification to drive the clock loads, right? So remember that one in this case. So this is about the circuit. The crystal oscillator circuit represents crystal oscillator circuit. Okay, but now in the actual situations, but in the actual situation, these VLSI chips receives one or more clock pulses. Okay, one or more primary clock signals from external clock chip. Okay, from the external clock chip. Okay. So usually all these VLSI chips receives one or more primary clock signals from the external clock chip and generates its derivatives. That means from this external clock chip, we are going to produce one or more primary clock signal. These primary clock signal generates derivatives of its derivatives to its internal use. Okay. So there is another thing you have to remember. Okay. So that means we are having a single clock sheet. From this clock sheet, we are going to generate primary clock signals. And from the primary clock signals, we are going to generate derivatives of the derivatives of its signal, clock signals. It be for the internal use. Okay. So internal. So it is often, and also it is often necessary to use the two non-overlapping clock signals also. Okay, sometimes it is also required such that the use of two non-overlapping clock signals. What is the meaning of non-overlapping clock signals? If you take the logical product of these non-overlapping clock signals, the result is 0 for all the times. Okay, that is the non-overlapping clock signal. For example, I am going to show here. Okay, so this is the non-overlapping clock signal can be generated here. So by using this type of signal, okay, by using this type of circuit, we can produce non-overlapping clock signals. Okay, that means here when it is pulse is getting 1 here, so at t is equals to t1, so at t is equals to t2, we'll get another pulse. Okay, because this is, assume that this is the latch or delatch, for example. Okay, so when the signal is here, the output is Q and Q bar. So this Q and Q bar will get like this. So this is the clock signal. And from this clock signal, we are going to generate two non-overlapping signals. Okay. So therefore, this circuit produces, generate the two clock pulses, clock 1 and clock 2, from the original clock signal CK. Okay. Similarly, we are having another circuit that is this is the another circuit in this case, which shows the clock decoder circuit. This is the basically clock decoder circuit that take the primary clock signals and generate 4 phase signals here. Okay, take the 2 primary signals and then generate 4 phase signals. Okay, so from these 4 phase signals, the phase signals are also shown here. And since the clock signals are required almost uniform over the chip area, so all the clock signals requires uniform over the chip area. So it is desirable to distribute all the clock signals with uniform delay. Okay, so generation is completed now. Let's go for the distribution. So once since the clock signals are requires almost uniform over the chip, almost to distribute all the clock signals with uniform delay. Okay, all the clock signals must have uniform delay. So this type of distribution network is, you can consider uniform delay. That means whenever the signal distributed to all the stages of the network, the internal circuit, so what happens? The delay must be same. Otherwise, there is a problem here. Okay. So in order to go get the same delays in this case, so therefore, in order to generate this type of signals, we require that means this type of distribution network network structure is shown here. There is nothing but we can call it as a H tree. Okay, here the distance from the center center to all the branch points are same. Okay, distance from the center of this one to all the branch points. So this is one branch, this is one branch, like this. Okay, so the distance must be same. Okay, distance must be same. So therefore, when the distance is same, so what happens? The delay that is generated for all the branch signals will be same. Okay, but what is the problem in this case is the structure is somewhat very difficult to implement in practice. Okay, this type of structure is very difficult difficult to implement in practice. So because of routing and routing constraints and the different fan out requirement. Okay, different routing constraint and also different fan out requirements. So this circuit is very, very difficult to construct. And a more practical approach for the clock distribution is to route the main clock signal to a micro blocks. Okay, to route the main clock signal into a micro blocks and use that local clock decoders to balance the delays under the different loading conditions. Okay, so that is the main important. That means the more practical approach for this clock distribution is to route the clock signal to micro blocks and use the whatever the local decoders we are having. So we can use that local decoders to balance the delay under the different loading conditions in the circuit. So in order to handle high fan out loads, okay, to handle high fan out load, the clock signal must be buffered. Okay, so there is also another thing in this case you have to remember. Okay, to handle high fan out loads, because the fan out is also very, very important. Okay, to handle this high fan out loads, the clock signal must be buffered in the multiple stages. Okay, now let us consider the other figure depending upon that. Okay, here. So this is the 3-level buffer circuit. Okay, this is the 3-level buffer circuit. This is the first level, second level, and third level. So just now here, the fan out of this inverter is 3. Okay, the fan out of this inverter is because the output is connected to 3 inputs of the other gates. Okay, so therefore the fan out of this inverter is 3. Similarly, the fan out of this inverter is also 3. The fan out of this inverter is also 3. The fan out of this inverter also 3. That means we are having multiple stages like this. Okay, so that is the main thing in this case. So here that means here this is the buffer we can consider. Inverter is not buffer. So every buffer stage drives the same number of fan out gates. Remember, same number of fan out gates, so that the clock delays are also balanced in this case. So this is like this. We are going to distribute the clock signals in the register system. Right. So the next class we can go directly to and we are having some points depending upon all these things we can discuss. Now in the next class we can go for the latch and its prevention. Already we discussed the latch in the first chapter. Okay, latch up and also its prevention. So what is the latch up? We will discuss in the next class. Okay, so already we discussed in the first chapter. Once again, we can go for the latch up and its prevention. Okay, so I'm going to stop the screen now. Thank you.